Side tone is audible feedback to someone who is speaking. The term is most used in the telecommunication field. In telephony, side tone is the effect of sound picked up by the telephone's transmitter, mouthpiece, and instantly introduced at a low electronic signal level into the receiver, earpiece, of the same handset, a form of feedback. Side tone in 19th century telephones varied until the carbon transmitter was used, which produced a distinct side tone that discouraged speaking loudly enough, and occasionally so loud as to cause the instrument to produce uncontrolled oscillations, resulting in howling audio effects. Side tone is disabled when phones of any kind are running in speakerphone mode, due to perpetual and almost immediate feedback. Anti-side tone circuitry incorporating the principle of the hybrid coil brought side tone under control in the early 20th century, leaving enough feedback signal to assure the user that the phone is really working, and allowing the use of a unitized telephone handset. In cellular technologies, one of the many benefits of side tone-enabled phones is that a user knows a call has been dropped or ended if he or she no longer hears side tone. Almost all landline, wired and wireless, phones have employed side tone, so naturally it was an expected convention for cellular telephony, but is not standard by any means. Usability experts believe that lack of adequate side tone causes some people to shout or speak too loudly when using a cell phone. This behavior is often referred to as cell yell. Side tone is valuable for the hearing impaired. The amount of side tone typically found on landlines is 8%, and is 4% for cellular phones. Side tone can be, and often is, amplified for landline phones for the hearing impaired. In VoIP technologies such as Skype, side tone has been experimented with but has not been formally adopted by software or hardware and accessories creators. Several software packages and wiring workarounds have been developed that replicate side tone, but feedback looping remains a problem. In wireless telegraphy (WT) and amateur radio, side tone is the audible indication of a continuous wave (CW) signal as the operator sends Morse code. As in telephony, side tone serves as feedback to the operator that what they are sending is what is intended. It is designed to mimic the tone generated by a typical radio receiver when a CW signal is converted to the intermediate frequency (IF), then mixed with the beat frequency oscillator (VO) frequency to generate a difference frequency, which is audible over the radio receiver loudspeaker or headphones. Side tone is also used on voice radio equipment to give the radio operator confidence that they are transmitting over the radio. The side tone audio is typically derived from the transmit audio circuitry. In aviation, the loudness of the side tone heard in a pilot's helmet or headset may be adjusted to suit personal comfort, although this may lead to communications problems since the pilot will be largely unaware of how his transmission sounds to the recipient. The ideal level for the right psychoacoustic behavior is reported to be about 7 dB below the received audio, according to RTCA specification DO 214. If the headset signal level is set too high, the pilot will inevitably speak more softly, resulting in too low a level of modulation to the radio transmitter. When a commentator, announcer, or mic for a public event may otherwise be able to hear their own voice in the delayed output from the loudspeakers, they may opt to use a headset which provides instant side tone of their own voice, thus removing the distracting effect of greatly delayed feedback from the loudspeakers.
About a phenomenon known as diode clipping, or audio clipping with the use of semiconductor diodes, how you can use two diodes back to back. Ordinary rectifier diodes will work at audio frequencies to limit the amplitude of the audio output of a device such as a communications radio. If you have been around radio for a long time, you may remember some of the older radio receivers which had no automatic level control or no automatic gain control, so that if you were listening to a very weak signal and you encountered a strong signal, that signal would blast you. The loudness of the signal would be overwhelming, And in fact, if you were wearing headphones, you might actually feel pain in your ears. Well, they used to devise a circuit in order to prevent this so-called blasting, and a very simple way to do that is to take two semiconductor diodes and connect them in reverse parallel like this. Now you may remember that a silicon semiconductor diode has a forward voltage drop of approximately 5 or 6 tenths of a volt. What that means is that a diode like this will not conduct until the voltage reaches that forward breakover voltage of about 5 or 6 tenths of a volt, and then after that, about at voltages, if you try to apply more than that voltage across it, it will act like a short circuit. So if you place two of these back to back in parallel, reverse directions, you can clip the peaks of any audio signal that comes in here to the input at this circuit here. You can clip that like this to about 5 or 6 tenths of a volt, and depending upon your the impedance of your headset or your audio output, that may occur at a rather loud level of volume, or it may occur at a very faint level of volume. The higher the impedance, the fainter the volume level at which this clipping will occur. But in practice, it turned out to work pretty well with ordinary headphones. And so in the olden days, when you were listening to the Morse code in particular on a radio, and a strong signal would come in, you could prevent it from blasting you. Unfortunately, if a voice signal is applied to this input and the voltage exceeds this forward breakover voltage here, clipping on a voice signal will produce distortion that can get so bad that you can scarcely even understand the voice. So this is like what you would use in an old-fashioned receiver without any automatic level control if you're listening to CW. They used to use it, CW meaning continuous waves or Morse code signals. Now you can also apply this same principle, reverse parallel of semiconductor diodes, to get a completely different phenomenon. However, you can also take that reverse parallel diode combination and connect it in series with the circuit. What you get in a case like this is something called a threshold detector. A threshold detector. Now what that will do is that if the signal voltage is less than about 6 tenths of a volt positive and negative peak, or 5 or 6 tenths of a volt, or 1 to 1.2 volts peak to peak, you won't get any output here at all. So if you're listening to a relatively loud Morse code signal and there's faint signals and noise in the background, you can in effect squelch out those faint signals. Another term for this is squelch. This is like an audio squelch. So it takes a fairly loud signal in order to get any output, and you can adjust the volume of your radio to determine how strong the signal has to be before it will get through this gate or this barrier. Here's an example of what the input and output waveforms would look like in a case like this. Same input as we had before, but a considerably different waveform. Notice that there's no output whatsoever until the input voltage reaches 5 or 6 tenths of a volt positive or negative instantaneous voltage. Once it gets above that, then the difference between the forward breakover voltage and the input voltage is what you get at the output. So you get again a distorted waveform, but if you're listening to Morse code signals, that distortion is not a particular problem. In fact, it's oftentimes a desirable thing to have a little bit of a nonlinearity in the audio circuitry of a Morse code receiver, because if you listen to a pure sine wave signal for audio signal for a long period of time, you can get considerable hearing fatigue. So This is another technique.
And today we're going to talk a little bit about squelch. The reason why we have squelch is multiple. First of all, in a channel where there are lots of communications, what's nice about squelch is that by positioning the squelch at a certain level, it prevents the static from being heard and lets the signals that you want to hear go through. So that's cool, because if it wouldn't be there, then we'd have this static all the time in between conversations. That's kind of annoying. So squelch is there for that, first of all. Second of all, squelch is there because the receiver will not scan unless it doesn't see a signal. And the only way for the radio to see there's no signal is by putting the squelch at a certain level. By putting the squelch at this certain level, you'll be able to let the receiver know when there's nothing, and it's going to actually know when there's a signal. So when you scan, an example here that I'll show it here with my R20. If I put my squelch open, which I just did, and I want to scan, it doesn't. It doesn't because the squelch is on, so it thinks there's a signal. So by putting the squelch to the lowest setting, when I scan, then it starts scanning, because now it can make a difference between when there's a signal or not, thanks to the squelch. The squelch setting is very important. Here in this radio, when I press the squelch button and I want to turn it off or on, it has different levels. It's here you see level 1 to level 9, and of course we've got open. Open means there's no squelch at all. In a more regular scanner that you have every day, you have usually this squelch button that is on top of the radio, and it's basically a little tuning or kind of a variable resistor that you turn. Technically, you want to set the squelch to the lowest setting that you can put it at, where the static stops. So for example, I want to set the squelch here. I'll just start turning it, and as soon as the static stops, I'm going to stop turning the squelch button. The reason why you can't put the squelch too high is the higher you put the squelch, the stronger the signal needs to be in order to actually be heard on the radio. So if you put your squelch level very high, you won't hear a lot of signals. By putting it just at the threshold, in that little line between where there's static and there's no static, you know that in general, if you're scanning for signals, even the weak signals will be able to be heard through the squelch. And that's very important, because when you scan with a scanner or radio scanner, you just want to make sure that you don't miss out on any signals. So by setting it at a very low setting, you know that even if the signal is not very strong, you're still going to hear everything that's happening. And of course, on some scanners, sometimes with signals that are very strong, you might want to set the squelch a little higher to prevent, for example, some interference. Maybe you have a local noise and your noise level is a little higher. Then by putting the squelch a little higher, you will prevent the noise from actually being heard through the radio, and any signal that's higher than the noise floor around you will be heard on the radio. So squelch is very important. In general, you want to set it at the lowest setting possible, not really much more than that. So hopefully you gave you an idea on how the squelch works and why you have it on the radio. And of course, why would you like to turn off the squelch? If you're dealing with extremely weak signals, then you might want to take it off, because some very weak signal just barely above the noise floor might not be strong enough to actually be heard if you put the squelch on.